I will start with some announcements and housekeeping things. The resources about this webinar and slides and recordings will be made available at the CGC website. Please save the date. These webinars happen on the fourth Wednesday of each month at 2 p.m. And please use the chat for any questions. We will have a question and answer session at the end of the webinar after the presentation. And we will share a link for surveys. So please provide your feedback. This really helps us with improving the webinar series and also get some topics for future sessions. With that, it's my pleasure to introduce the speaker of today's webinar, Dr. Wenming Zhao. Dr. Zhao is a lead bioinformatics scientist at the FDA and has advanced training in biology and computer science. He has numerous publications in several peer-reviewed journals, such as Nature, PNAS, and he received an NIH Director Award in 2010 in recognition of his contributions to cancer biomarkers discovery. Dr. Zhao was a principal investigator at FDA, and he led an international working group to establish reference materials, data sets, analysis pipelines, and quality metrics for cancer mutation detection with next-gen sequencing technology. And this has led to several manuscripts which are currently in press. In addition, Dr. Zhao was a lead reviewer for NGS-related diagnosis products and applications, including OncoPanel, whole exome panel, NIPT, and so on, and also for analytical software, which includes bioinformatics pipelines and some knowledge databases and so on. So he provides recommendations on regulatory decisions regarding the safety and effectiveness of medical devices for in vitro diagnostics. Currently, Dr. Zhao is the lead bioinformatics scientist at the Office of Oncologic Diseases, Office of New Drugs, Center of Drug Evaluation and Research, CDER at FDA. So without much further ado, over to you, Dr. Zhao.
Thank you, Sai, for the nice introductions. So let me just go ahead and share my screen. Can you hear me right?
Yes.
Okay. Can you see my screen?
Yes. Not the
Okay.
presentation. Perfect.
All right. Well, thank you. Thank you for giving me this opportunity to introduce a study result for the best practice of cancer mutation detection with whole genome and whole exome sequencing. I'm speaking this on behalf of the Somatic Mutation Working Group of SUQC consortiums. So this study has been accepted by Nature Biotechnologies, and it's going to be scheduled to be published soon later this year. So let me start my talk with this overview of the cancer mutation detections typically happening in any lab or clinical settings. So regardless what kind of sample type you get in, either cells, FFPE samples, or fresh frozen tissues, you always extract DNA and then running on NGS sequencing machines, and then run through all different type of application for you with bioinformatic pipelines. So really complicated pipelines. So we know that there's a war between the wet lab and dry lab, right? Sometimes it's actually not just simply war, it's actually probably different location, even different country. We also realize there's actually war in our mindset. That is, when people develop assays or tools for cancer mutation detections in a wet lab, they probably not pay too much attention on the dry lab in terms of how was the best pipeline for your assay, or vice versa, right? So people working on fine-tuning or develop new algorithms, they may not pay too much attention in terms of how the data will derive from. What if the algorithm works best for FFPE or for fresh frozen? So with that, we kind of remove this kind of war, so that we make a study design that try to capture in all possible variables through the whole process of the cancer mutation detections. By doing so, we chose two cell lines, match the tumor normal cell line from same individuals. The cancer cell line is for triple-negative breast cancer, and the normal cell line is derived from B lymphocyte that EBV transfer. Now, with these two cell line DNA, we actually did some modification in terms of cell palette. We can mimic the FFPE process and extract the DNA from FFPE process the DNA. So we have a fresh with FFPE DNA. We have 8 different sequence centers. Some center working on the different, reproducibilities or DNA input. Some center only did FFPE samples or the library preps. So with all these 8 different centers, we try to capture in. First thing is the library prep protocol, right? So we have 2-sig, 2-sig nano, and next tera flags. So with different DNA input from 1,000 nanogram down to 1 nanogram, right? So with all different input and with different library prep. We also try to mimic tumor purity or tumor content by mixed DNA of tumor spec into normal, and that we can reach to 75% tumor, 50%, 20%, 10%, 5%. And then we did also whole genome with whole exome. We try to do this, try to evaluate what repeatabilities in terms of intracenter, intercenter across different platforms, was i.e. whole genome with whole exome. We also try to evaluate library prep protocol. Again, we're showing 3 different protocol with different DNA input. We try to look at the tumor purity in terms of coverage, what's the detection limit with the tumor purity, right? And also what artifact that FFPE process can introduce during this library prep or during this sample processing. Besides that, we also try run all available tools or platforms on NGS and try to define the content or mutation content in terms of SNV, copy number, structuration, not only somatic, but also understand the germline with normal cell lines. And with that, we try to define high confidence call set, use that as a reference call set for the future that people can do benchmarking with our sample as a reference sample. We also did actually de novo assembling for genome from normal cell line DNA and try to define the personal genome for the somatic mutation detections. We already submitted one manuscript. Currently, it's under review. With all different variables in the workflow, starting from the sample type, library prep, DNA sequencing platforms, as well as the bioinformatics pipelines, we have overall generate over 1,000 call set. With this call set, we evaluate all those performance to the benchmarking. So, but first thing, what we do is evaluate the quality of DNA and also data set derived from whole genome and whole exome sequencing. And this is just showing basically the coverage of the whole genome sequencing. And here we just showing it's a key quality metrics that we think is important, and which called GIV. And we see that it's actually showing different in different library prep, and also showing that IGV have some impact or some monitoring about the FFPE processing. So what's GIV? GIV basically is name for global imbalance values. So what that means, because when we do pair and sequencing, right, we do sequencing from forward strain and we also did sequencing from reverse strain. So if we see the mutation, T to G mutation on one strain, we should see A to C mutation on the other strain. So the ratio of this T to G mutation with A to C mutation should be equal to 1. So this is what's showing here. Regardless is whole genome sequencing or whole exome sequencing, regardless DNA coming from cancer cell line or normal cell lines, they all should be around 1, right? The ratio should be around 1. But if you look at this particular G2T mutation was C to A mutation ratio, you actually see that this is remain 1 for the whole genome sequencing, right? Regardless the tumor or normal, whole genome sequencing still ratio is 1. But if you look at the whole exome sequencing, both tumor DNA, normal DNA was tumor DNA, both, both show the imbalance ratio. Like see, they have towards the G2T mutations. And this actually particularly associated with some library prep, not all library prep. And if we see this and associate them with the DNA inside fragment side, you actually can see that the GIV score is inversely correlated with the inside fragment side. The smaller fragment size, you get higher imbalance values. If the inside fragment size is greater than 250 base pair, you do not see this imbalance anymore. So why is it important? Because when you look at the mutation calling out from this library prep, you can see there's a huge bias towards C2A mutations in this case. All these C2A mutation bias actually correlate with here, global imbalance value. In other words, inversely correlate with inside fragment size. So what happened? What caused this? And actually, 8 years ago, there's a paper indicated when you're doing DNA fragmentation sonications, you did over sonicate the actual heat. Overheat can introduce in guanine oxidations to the DNA, and the damage will result in this artifact. Okay, so if with this in mind, and GIV score can be utilized to monitoring such artifact. Okay, so back to bioinformatics. When people are doing the concordance across different color, different platforms, they're just mainly using Venn diagram or bars, stacking bar, looking for the concordance, right? So if we have so many redundant repeat of the call set, how are we going to handle that? How are we going to display concordance across, let's say, 280 VCF files? So we come up a kind of idea like similar as what's called stacking bar, but we make a tweak so that we look into the concordance and look at the most number of concordance SNVs will be on top, the least number of concordance will be on the bottom. So you will see, you would like to see majority of SNVs will be concordant across all the call set, right? So that'd be good. If you see a lot of SNV in the bottoms, and in this case, touchdown on the ground is not good, right? So just like tornado, it's touching, it's only make damage when you touch on the ground, touchdown on the ground, right? So you see this, and we use in this tornado plot to evaluate the aligner. So we see this BWA MEM, majority of actually showing in the air, and we see the same shape for the both type 2, and we see the same shape for the normal line. Indicate these three pretty much behave similar, but if you look at SOAP, you see majority of SMVs is actually touchdown on the ground, means majority of SMVs by SOAP will be only unique with SOAP aligner, not the other three. So because of this, we drop the SOAP aligner in our bioinformatics pipeline. We only evaluate 3 aligner, BWA, both type 2, and normal line in our follow-on studies. So with that, we evaluate performance across the 6 sequence center. 3 center did triplicates, and 3 center did single run. So we have overall 12 whole genome sequencing run. And then you can see that the tornado shape is very uniform, pretty much the same. We did the same thing for whole exome sequencing in the 6 center. Again, for the 6 center, we did a 12 repeat total. But if here you see the shape totally different compared to whole genome sequencing, right? So you see a lot of SNVs only identified by this center only replicates, right? And we actually come up a formula to calculate this, we call it O score, overlapping score, and based on the concordance across 12 repeats. And based on this formula, we can calculate the number. And you can see that the number here very uniform and reach to around 0.88 or 0.9. But here we see very wide distribution of the O score. If you look at box plot of this O score, you can clearly see the difference between whole genome sequencing and whole exome sequencing. So let's suggest that for the whole exome sequencing, we are facing challenge of repeatabilities across different sequence center or even across different repeat within the same center. So with that, we continue evaluate aligner, caller, repeat, and compare the whole genome sequencing with whole exome sequencing. And you can see that for aligner, we do not see much of difference. Obviously here, we only evaluate both type 2 BWA and normal line. We exclude SOAP because we think SOAP is kind of outlier. For the caller, you see the caller is important. It's actually showing difference for the whole genome sequencing, right? And also great difference for the whole exome sequencing. The solid line is whole genome sequencing. The dashed line is for the whole exome sequencing. And for the individual repeat of 12 libraries, you clearly see the whole genome sequencing quite consistent and uniform. But for the whole exome sequencing, you see the 12 repeats are quite dramatically different. We also using statistical analysis to showing that for the whole exome sequencing, there are lots of factors can attribute to the repeatabilities, including caller coverage, GC content, GIV score, inside site. And as you see, these are confounding factors for these two, and also a combination of all these variables. But for the whole genome sequencing, the only factor affecting repeatabilities across different center, different library prep is the caller. Okay, so you see the difference between whole genome sequencing and whole exome sequencing. Now, with that, we still not show clearly what's the advantage, what's the repeatability, right? Because we're using concordance only. So the best way to evaluate performance is try to define the call set or reference call set. If you know the true set, we then use the true set as the denominator to determine performance. And this is what we do here. We take advantage of multiple repeat across sequence center, across different library prep, across different sequence machine. Here we have high-seq repeats. We also have 9 repeats from normal-seq. We combine all these 21 runs of the whole genome sequencing and then apply 3 different aligner. So we have total 63 band file. Right, so we take this 63 band file and apply 6 caller. So we have multiple data set, multiple aligner, multiple caller, and using consensus to try and build a model. We have 2 different model building algorithm. One is the somatic seq workflow. The other one is using neo-somatic. So with both the different algorithms, we be able to evaluate and define the variant code or mutation code. In this case, we only limited to this single nucleotide variation as well as small indels. We'll be able to define high confidence, low confidence, or unclassified based on evidence. Right? So how many evidence showing in this repeat, how many evidence supporting this variant code in different code set. So this study has also been accepted by Nature Biotechnology. We're going to be co-published these 2 papers side by side in later this year. So we did some validations. Okay, so here is just breakdown. So we have overall about 40,000 we call the true set SNVs, small indels. This is combination of high confidence and also medium confidence group. And we have also have some low confidence call set and unclassified. You can see that the no confidence and some of unconfident we did not include here. The low confidence side more or less is just due to the mutation frequency. Right? So that more or less due to library prep. Sometimes library prep including this mutation because low frequency of mutation in the DNA in the genomic DNA. We did 4 different ways to validate the cause set, 40,000 SNV indels by in silico. In silico means we have a spiking DNA tumor DNA into normal, so we know the ratio, and we're looking for the MAF or VAF changing in the different tumor content and see whether this changing will align with the dilution. So we come up a fitting score. So the higher fitting score means that the more reliable or fitting the dilution series. And you can see that for high confidence core set and medium confidence core set, we have really good correlation with the fitting score, but not for the no confident or unclassified group. We also randomly select a few hundreds the SNVs within these 4 categories. We did PCR based empiric sequencing, and then and you can see that for the high confidence, medium confidence, we get really good correlations and confirmation by empiric, but not so much for the unclassified or no confident or low confidence level. We also did another sequencing using exon sequencing, but using iron terran and whole exome sequencing with HiSeq. Both platforms indicate that for the SNV defined in high confidence, medium confidence group, a very good correlation rate and confirmations. So we are confident about the 40,000 SNVs in there we defined as a reference cost, and hereby we using this as our benchmarking reference cost set. So once we define the reference cost, we'll be able to further benchmarking the performance. In this case, we're looking for DNA input library prep protocol. So again, with different library prep protocol, the ChooSeq, we have DNA input from 1,000 nanogram to 250 nanogram. But ChooSeq Nano, we can have DNA input as little as 1 nanogram, and send as next era. And you can see that for ChooSeq Nano, 1 nanograms is not good enough, right? So we have suffered dramatically in terms of coding accuracy with 1 nanogram, regardless if either mutate 2 caller or striker 2. But if you look at the next error with 1 nanogram DNA input, we see the performance is equally well to 100 nanogram or even with 1,000 nanogram using ChooSeq. Right. So we're very happy to see that within as little as 1 nanogram, we still be able to get the performance as the 1,000 nanogram. And also here we compare the FFPE sample with fresh frozen DNA. You clearly can see that fresh frozen is good, reliable. If using FFPE samples, you see the precision, accuracy, and record is actually suffered tremendously. We also evaluate bioinformatics components indicates including the rich pre-processing, because there's several reports that and the tools available that can fix the artifact. Remember, we have global imbalance value, right? So this is the artifact, and you can see that with the BCF2, we can remove this artifact. However, you can also see that we're introducing new artifact here. So that's why in our paper, we cautiously warning and using the error fixing tools. Make sure that if you're fixing error, you're not introducing any new error, new problem. We evaluate the joint effect between the aligner color. In this case, Straker 2 works the best with the PWA aligner, but not so with the bow tie tool or normal line. With normal line, it's kind of the um, kind of the increasing the recall rate, but actually suffer the precisions. But with bow tie, it's kind of more conservative. And we think this is correlated with the mapping quality score because the PWA mapping quality score is mostly between 50 and 60, but the normal line is actually have higher mapping quality score and such, resulting that you have overcalled son of mutations and then resulting in some maybe false positive. We also evaluate the JTK components that for these Indo realignment and quality recalibrations. Some people think this is critical because they can reduce the false positive, especially for the mutational indels within the polyholymer regions. And we evaluate that with 3 colors, MUTAC2 and Straker2 and Somatic Sniper. And you can see that for Straker2, the JTK process doesn't see much of influence, right? So we do not see much of gain or loss or overlapping. MUTAC2, we see some impact, but the most impact is on the Somatic Sniper. And we think this is important that when you using the color, that depends on what color you're using. And for Striker 2, it's actually doing the indoor realignments during the calling, uh, during the calling algorithm. So you don't need to do this GATK indoor alignment anymore. But for the Somatic Sniper, you probably need to do pre-process or post-alignment processing with GATK2. We also evaluate the tumor content, coverage, and color. In this case, we evaluate 5 color: Lancet, MUTAC2, Straker2, TN scope, and those of Somatic Sniper. We here only used 20% of tumor content was 50% tumor content. And you can see that with tumor content as low as 20%, increasing coverage definitely will benefit your calling accuracies and the recovery rate, right? But if you have tumor content greater than 50%, the increase in coverage may not be as helpful as you expected. In some cases, actually have some that adverse effect that you will be surprised to see. In this case, for example, MUTAC2, if you have 200x coverage or 300x coverage, your calling accuracy actually dropped. And that's actually due to the way that MUTAC2 can call in the mutation during the random selection or kind of random downsampling the race because they cannot handle too much of the coverage rates. So finally, we evaluate the repeatability, actually repeat, biological repeat versus analytical repeat. Well, analytical repeat means you have single runs, but you run multiple caller. In the case, let's say you run MUTAC2, you run Somatic Sniper, you run the Straker 2, and you try to get consensus of calling and get better result. Obviously, you can get better accuracy result, but you will lose a lot of mutation, true mutation, because the consensus is actually you only look at a very subset of the true set. But within the biological repeat, which is here, it's obviously better than individual runs, right? So you with your different library prep and you call them separately and using consensus, you definitely can increasing your calling accuracy, but also have some job in terms of recall rate, but not as such as much as the by informatics or analytical repeat. So we recommend that if you have if the cost is not limit for your research grant or research project, you may prepare multiple library prep, either pooling them or just calling them separately. Here we also suggest showing that for the whole exon sequencing is more widely distributed in terms of coverage. You can see that even though we intend to target 300x coverage or 100x coverage, you can see wide distribution across the whole exome regions. But for whole genome sequencing, if you intend to cover 100x coverage, they pretty much uniform covered throughout the chromosome. And also for the artifact by 3 different color, Mutex2, somatic sniper, and Straker2, you can see the artifact or false positive for Mutex2, Straker2, mostly at the low frequency. But for the somatic sniper, there are lots of artifacts actually with high mutation frequency. That indicates this algorithm issue, not because the distribution of the mutation rates issues. Okay. So in the end, we come up recommendations for the best practice with whole genome sequencing, whole exome sequencing, including library prep, library DNA input, library construction protocols, and choice of the NGS platforms. I don't want to go through individual, but if you have time, you can go to our paper on the bioarchive. And also maybe when it's come up, publish it on the Nature Biotechnologies. We also recommend the reach coverage and also recommend some QC metrics for the quality control. Reach alignments, we do not see huge impact in between the bow tie to PWA and normal line, but watch out those the mapping quality score because they have different range, different scale. Post-alignment processing, GATK, we think it's important for some color, but not necessarily for some other colors that already have built-in the alignments algorithm. For the mutation calling, we think there are different options, but some options is better for one platform. For example, Straker2, we think is more reliable for whole genome sequencing, but it's so sensitive, so it's easy to pick up any artifact from whole exome sequencing. For the pipeline construction and change in protocol, we think overall the whole processing is an inherently integrated process. So any change to any component should be validated. It is no simple as a plug and play. So whenever you make thinking to change in your pipeline or component of your pipeline, you will need to find a way to validate, and then need to validate from end to end. It means starting from sample prep to final reporting your variant. So so again, I would like to emphasize that this is a team effort. The working group started the end of 2016. By the end of the 2018, we have almost 200 members and from these 60 plus institutes, and we have a great team leadership here. Many people come from different institutes, different entities, contribute and lead this project. With that, I will finish this with this disclaimer. Since we have two heads, right? So we have regulatory, we have the research, but here what I present here is only for research study. It's not intended for guide to clinical applications. The view present here do not necessarily reflect current or future opinion or policy of the U.S. Food and Drug Administration. Any mention of commercial product is for the clarification, not intended as endorsement. Finally, I list the data availability here. So we deposit all FASTQ file on SRA. We also have a designated NCBI FTP site for BAM file, for the VCF file, for any other associated data file or code. And finally, we also have a BAM file on CGC on the SCQC2 project. With that, I can stop here and ready for questions.
Great. Thank you so much, Dr. Zhao. This was a very, very useful and incredible presentation. So before we go to the question answer session, Dan has just posted a link to a feedback survey. So please, all the attendees, we request you to fill in the survey. If you have questions, please post in the chat. And I have a couple of questions that I received, so I'm going to start off with those. So can you comment on the how does this study impact evaluation of trial drugs and help with overall precision oncology?
Yeah, that's a good question. Again, I don't want to speak for FDA because I'm work for FDA. I used to review the NGS related device. So I only speak myself. So I think what we did here has been helpful for us, at least looking for the performance, those the QC metrics, for example. What are those key QC metrics which we can look into and make sure that the data quality is good, and also with that how we can ensure the performance, right? So we know there's some impact in terms of the library prep, in terms of protocol, but also there's some impact in terms of the side-to-side variations, right? And the human handling issues. So that's something that we still cannot avoid, but the overall the impression or the conclusion from this study is the less step that you do in the experiment, the more reliable outcome become reproducible, right? So if with the whole exome sequencing, you have steps of the sonication, you have step of capturing, you have step of the purification of a PCR fragment. So that creates huge potential that increasing the or reduce your repeatability. So in general, in practice is, okay, if you really want to identify mutations and you really think it's important you find the true mutations, right? And then you need to think about, okay, what's the best strategy to do this experiment, either using panel or using whole genome sequencing. Depends on what's your angle, right? So the whole genome sequencing will limit your detections capability, like the limit of detection, right? So with only 100x coverage, you may be able to detect 5% of the mutation frequency. But with capturing, you maybe can detect as low as 1%. So it depends on your goal. If you're for research purpose, you maybe try to cover as broad as possible, but for the diagnosis, you may be focus on accuracy and the detection sensitivity.
Great. And I think the table that you showed at the end is very, very useful, and it can be used as a reference for when people start their projects. Okay, great. We have another question that was posted in the chat to us. I'm wondering why new somatic is not included for comparison in your analysis.
Yeah, so because of the time, right? The new somatic just coming offline a couple of years ago, and this project started way before neosomatic. And we actually using neosomatic for another benchmark study, which you already submit in the paper. So which you can be maybe companion publication, but in different journal. So we just stay tuned. We will have benchmarking study result with neosomatic.
Great, thank you. So the next question we have you examined the reproducibility of calling heterozygous variant calls versus homozygous? in particular in relation to tumor purity? In other words, how reproducible is the actual VAF?
That's good questions. Well, we in our SMV course set, we have a huge number of the SMVs consider homozygous, but we think it's not homozygous. It's actually due to LOH, lost heterozygosities. So we did have copy number. We actually, in the paper, we did tie it up with the SMV frequency with the copy number, and you can see that clearly see the patterns. You can see the patterns of not only just copy number, but also you see, let's say, I have a set of mutations called that in the copy number equals 3, but I can see the pattern of VCF, VAF, the pon 1 and pon 6 and 5 and pon 3, right? So you can clearly see this pattern. With 3 copy of the chromosomes, you actually can see a fraction, 1/3, 2/3 of the mutation frequency. So that's actually correlate very well.
Great. We have another question. We have FFPE tissues for research use, and they're usually very old. So, what do you suggest to obtain good data?
Yeah, that's still, even though we did some study here, but still very challenging. We think FFPE sample is inevitable. I mean, still lots of people using FFPE for clinical, for research. But the one thing I can see that using FFPE, the artifact coming from FFPE normally have low allele frequency, VAF. So if you're not looking for biomarker with MF, VAF less than 10%, you may be safe to avoid FFP artifact. But also there's some trademark from FFP artifacts, so you can try to avoid follow on those mutation with those trademark of the mutation characters.
Wonderful. Okay, while we wait for other questions, I have one more questions. So can you comment on how you use the Cancer Genomics Cloud for this analysis?
Yeah, that's why I take this opportunity to thank Seventh Bridge to providing the credit to using CGC Cloud to support this SAQC effort. So we think it's very useful for us because this is, again, you can see that from working group members. They're actually across all different corner of the world, right? So we have people from China, we have people from Europe, we have people from the US, East Coast, West Coast. So we have different people from different time zones, and how we can take advantage of this is challenging, and we appreciate CGC give us a platform so that we can put our data on CGC cloud, and people from different location can run the analysis, develop a tool there, and then report in the outcome. So it's tremendous help for us to facilitate our and also coordinate our research and data analysis effort.
Great. And one more question I have from one of the users, one of the attendees. So how did you decide on the different library prep methods to use?
Well, we take normally what people are using, right? So at the beginning, when we start out this project, ChooSeq is pretty much universal, right? That just come out not long ago. And later on, Illumina developed the ChooSeq Nano, and we think, oh yeah, let's try. And later on, Illumina come up another protocol with the next Terra flags. So we say, okay, let's try to compare 3 library protocol that we think it's going to be useful, and also looking for DNA input. And let's say sometimes 1 nanogram is actually out of the range, recommended range. So we say, let's push the envelope a little bit to see how low we can go. So that's why we try 1 nanogram, and we're happy to see that even 1 nanogram, in some cases, we still can make it workable.
Great. I have one more question, which is my own question. So, what do you envision as the future direction of this project?
Yeah, we actually working on second phase of this project. First thing is we try to make DNA as much as possible to support the needs for the community. And second, we try to further improve our core set, right? So we still think there are lots of room to improve. Maybe you can incorporate some latest technology, such as the packable hi-fis or long reads technologies. And the other thing is we try to expand our portfolio into other cancer types. Here, this is triple-negative breast cancer cell lines. We try to work with the ATCC and see whether any other cell lines for different cancer types, such as lung cancer, colon cancer, we can expand our portfolio to have a more reference material, reference data set for the community.
That sounds great. Yeah, I can even think of, if it's all available, your paper is going to be published, but if it's all available in a single place, that will be really valuable for researchers when they plan their studies.
Yeah, that's the goal. I think this is also maybe important for people develop the IVD device. So there's a requirement for analytical study, and for doing analytical study, having a common reference samples to perform those analytical study is actually quite important. And also we have a built-in tool set so that we kind of have standardized the for the benchmarking performance, right? So that in that word, people can use the same sample, and we can evaluate them or treat them fairly with the same data set.
Wonderful. So we're very excited to see your papers published later this year. We have one more question, but I have requested a clarification. I didn't quite understand what the attendee asked. So he's asking, consider some of the commercial software. So I don't understand exactly what he wanted.
Commercial software. Most of software we use in the study are open source.
Right.
We do have a commercial software called TNScope. That's with the sponsorship from the Centennial. But we think open source is very valuable resource, right? So, but again, we need be careful using any new tool coming out. Make sure you have fully understand the performance, right? And also under what conditions this software is better performed, right? So before you truly apply that to your productions, you need to do some benchmarking study and with some confident data set.
Got it. I think you answered. So the attendee clarified, in the next phase of the pipeline, will you include commercial software? So I think you spoke about how open software, using them is more valuable.
Well, we evaluate all software, including Illumina Dragon pipelines, which we're going to include in our benchmarking study for the neosomatic. Okay. So well, again, we have limitation in terms of access to commercial software. So we cannot get, if we don't want to spend money on the commercial software unless they're providing free license to us.
Got it. Thank you. Okay, so this has been really very helpful. We are looking forward to your papers. And just for everybody, somebody had asked about the recordings. It's going to be available in the Cancer Genomics Cloud website. And next month, we have Dr. Wilson McCarroll from NYU Grossman School of Medicine. So Dr. McCurrow is a postdoctoral fellow there, and he's going to be presenting on line one research in collaboration with the Seven Bridges Cancer Genomics Cloud. So he's going to be talking about how he linked RNA-seq data from GTEx to his L1EM tool on the CGC to survey line one expression outside the context of cancer. So please be on the lookout for these announcements. The announcement page is already available in the Cancer Genomics Cloud website. And thanks everybody again for joining us. And thanks so much, Dr. Zhao, for presenting your work today.
Thank you for having me.
Absolutely, our pleasure. All right, bye. Thanks,
Bye-bye.
everybody.